Hello everyone and welcome in the 20th lecture of control system. So in last lecture we discussed the types of poles. Now let us discuss the significance of poles in control system. This is one of the most important lecture in the basics of control system. So from the poles of transfer function, what information we can get, we are going to discuss in this lecture. So, from the poles of transfer function, we can find the stability of a system. Then we can find the time constant tau of system. Also, from the poles of transfer function, we can find out the frequency of oscillations, then the type of a system and the order of a system. So these are all important things that we can find just by knowing the poles of a transfer function. In this lecture, we will discuss the stability of the system. If we know the poles of a transfer function, how can we find whether a system is stable or not? And in next lecture, we will discuss about time constant tau and frequency of oscillations. So I request you watch the entire lecture so that you get a good knowledge about the poles and stability of the transfer function. So let us start with the first point, that is stability of a system. Now first we have poles on left hand side of S-plane. So I have a transfer function which is given as x of s is equals to 10 upon s plus 2. So we know the roots of denominators are the poles of a transfer function. If you substitute s plus 2 is equals to 0, you will get the pole at s is equals to minus 2. Now we can plot this pole on the S-plane. We have the S-plane which is the sigma plus j omega axis. Sigma is the real part, j omega is the imaginary part. Our pole is at s is equals to minus 2. So we can draw here a pole at s is equals to minus 2. So this is the plot of a pole on the S-plane. The pole is on left hand side of S-plane. Now we have to comment about the stability of this system. So if we have a pole which is on the left hand side of the S-plane, we need to comment upon the stability of the system. So in order to go in detail, first let us find the inverse Laplace of the given transfer function. So we have x of s which is 10 upon s plus 2. Its inverse Laplace will be x of t. Inverse Laplace of x of s will be x of t, and the inverse Laplace of 10 upon s plus 2 will be 10 e raised to minus 2t into u of t. Now how to find the inverse Laplace? We have already studied in the lecture series of Laplace transform. Those who have missed or not seen the lecture, I will share the video link in the I button. You will understand how to find the inverse Laplace of a given Laplace transform. So the inverse Laplace of 10 upon s plus 2 is 10 e raised to minus 2t u of t. Now we have to plot this x of t. Now at t is equals to 0, x of t will be it is 10 e raised to minus 2, value of t is 0, so it is 0 into u of 0. So I will get 10 e raised to 0, e raised to 0 is 1, so 10 into 1 into value of u of 0 is 1, so the value of x of t at t is equals to 0 will be 10. Similarly, the value of x of t at t is equals to infinite will be x of t, the value of x of t is 10 e raised to, I can write minus 2 into the value of t is infinite, so I'll directly write minus infinite into u of infinite. So I will get it is 10 into e raised to minus infinite is 0 into u of infinite is 1. So the value at t is equals to infinite will be 0. So the value of x of t for t is equals to infinite will be 0. So now we have the values for t is equals to 0 and t is equals to infinity. We can plot x of t. Now if you compare this x of t with e raised to minus at, this will be an exponentially decaying signal. At t is equals to 0, the value is 10, and as the time increases, at infinity, the value will be 0. So this is the plot of x of t is equals to 10 e raised to minus 2t u of t. So 10 e raised to minus 2t u of t is absolutely integrable. This signal, you can integrate it from the value at t is equals to 0 to t is equals to infinite. The signal is a finite signal, hence we call this signal as absolutely integrable, and this is an bounded signal. So whenever a signal is absolutely integrable and it is bounded, then the given system is a stable system. So we can say if all poles lies on the left hand side of S-plane, then the system is a stable system. Also, the location of pole was on real axis. Our pole was at S is equals to minus 2. This was my pole. The pole was on the real axis and the nature of response was exponential. Our response was exponentially decaying like this. This was our response. The value was 10 e raised to minus 2t u of t. So this is an extra information. When the location of pole is on real axis, then the nature of response will be exponential. So I hope you have understood if all poles are on the left hand side of S-plane, then the system is called stable system. Why? Because the response is absolutely integrable and the signal is also a bounded signal. When these two conditions satisfies, then the system becomes a stable system. So our next point in stability of a system is pole on right hand side of S-plane. Now let us see if we have a pole on a right hand side of S-plane, then what will be the stability of the system. Now let us consider one example. I have a transfer function x of s is equals to 10 upon s minus 2. Now if you substitute s minus 2 is equals to 0, you will get the pole is at s is equals to 2. So the plot of the pole for s is equals to 2 is like this. The pole is a real part and it lies on the right hand side of the s-plane. Now to comment about the stability, let us find its inverse Laplace, that is x of t, and first we will plot the x of t and then we can comment about the stability of the system. So my transfer function was x of s, which was 10 upon s minus 2. Its inverse Laplace will be x of t is equals to 10 e raised to plus 2t u of t. Now again, the value of x of t at t is equals to 0. Let us find x of t is equals to 10 e raised to, we have 2t, so 2 into 0 will be 0 into u of 0. So 10 as it is, e raised to 0 is 1, u of 0 value is 1. So the value of x of t at t is equals to 0 will be 10. Similarly, we can find the value for t is equals to infinite. So I can write x of t is equals to 10 e raised to 2 into infinity, that is at infinity, into u of infinite. So I will get it is 10 e raised to infinite is infinite into u of infinity is 1. So I will get the answer. The value of x of t for t is equals to infinite will be infinite. Now since I have the 2 points at t is equals to 0 and t is equals to infinite, I can now plot the signal x of t. So the x of t will be exponentially increasing signal. The value of x of t at t is equals to 0 is 10, and as the time t is increasing, the value is also increasing, and at t is equals to infinity, it will reach to infinity. Now this signal is not absolutely integrable and it is an unbounded signal. So if you want to find the value of this signal, it is not possible because the signal is an increasing signal. The signal doesn't become zero at any instant of time. So this signal is not absolutely integrable and hence it is an unbounded signal. So we can say if any pole lies on right hand side of S plane, then the system is an unstable system. So why it is an unstable system? Because when you plot the x of t, the signal will be not absolutely integrable and the signal will be an unbounded signal. Hence, any pole on right hand side, the system is an unstable system. Again, the location of pole was on real axis. This was my pole. My pole was at x is equals to plus 2. So the location of pole was on real axis. And the nature of response was again exponential. We got the response something like this. So this is an exponential signal. So whenever the location of pole is on real axis, the nature of response is exponential. So let us go to the third point. That is a single pole at origin. So if we have a single pole at origin, then what will be the stability we will see? So I have a transfer function x of s is equals to 1 by s. If you substitute s is equals to 0, you will get a pole at s is equals to 0. And the pole diagram will be like this. The pole will be at s is equals to 0. Now in order to comment about stability, first as usual let us find the inverse Laplace of x of s to get the value x of t. Now we have the value x of s is equals to 1 by s and we have to find the inverse Laplace transform of x of s. And we all know the inverse Laplace of 1 by s is the step signal u of t. So we can directly plot the signal u of t. We know how to plot the signal u of t. It is a step signal. We have already discussed about step signal in the previous lectures. So now u of t is a special function and whenever you have u of t, the system is marginally stable. This is a special case of stability in which a u of t signal is a marginally stable system. So whenever you have a single pole at origin, the system will be marginally stable system. Now let us see the fourth point. It is double pole at origin. That means if you have two poles at origin, we have the transfer function x of s is 1 by s square. With the poles will be, we will be having two poles, first pole at origin and second pole also at origin. So this is my S plane, sigma versus j omega. I have my first pole at origin and I have the second pole again at the origin. So I have two poles at origin. Now let us see whether this is a stable, unstable or marginally stable system. Again, to check the stability, first we will find the inverse Laplace transform, that is we will find the value of x of t. So the inverse Laplace of 1 by s square, we know it is a ramp signal r of t. So we can draw the signal r of t. We have also discussed about the ramp signal in our previous lectures. Now again, if you want to integrate this signal, it is not possible because the value of the signal is increasing as t is increasing. Hence, it is not absolutely integrable and it is an unbounded signal. So whenever the signal is not absolutely integrable or it is an unbounded signal, we can say if any double poles lies on origin of S plane, then the system is an unstable system. So a single pole at origin, the system is marginally stable, but if we have two poles at origin, then the system is an unstable system. So now let us go to the complex part, which is the fifth point. We have non-repetitive poles on imaginary axis. For example, you can take the Laplace transform x of s is 1 upon s square plus 1. If you substitute the denominator to 0, you will get two poles. First pole will be s1 is equals to plus j1, and the second pole s2 will be at minus j1. Now few students must be having the doubt how we got the value of poles as plus minus j1. Now in this lecture, I am not finding the poles of the transfer function. Once we finish the significance of the poles in control system, we will solve some good previous year GATE and engineering services questions. There I will discuss how to find the poles of a transfer function. So we have two poles S1 and S2 at plus minus J1. So we have to plot this on the S plane. So the first pole is at plus J1 and the second pole is at minus J1. And our heading is non-repetitive poles on imaginary axis. Now we have to comment about the stability when the poles are non-repetitive and they lie on the imaginary axis. So we will follow the same procedure. First, we will find the inverse Laplace transform of 1 upon s square plus 1. So the inverse Laplace transform will be x of t is equals to sine t u of t. Now many of you must be having the doubt how to find the inverse Laplace transform of the given function. Now we have already discussed in the Laplace transform series. I will give the link of the Laplace transform series in the I button. If you want, you can just go and watch the lectures. Just for an example, now the Laplace transform of sine omega naught t u of t is omega naught upon s square plus omega naught square. Now if you compare these both equations, our omega naught is 1. So here we have to write omega naught is equals to 1. So we can get inverse Laplace as sine omega naught is 1. So I can simply write t u of t. So this is the same answer what I have written, sine t u of t. So this is the way you can find the inverse Laplace of the basic signals. As I told you, when we will solve some good questions on this topic, there you will get a good idea on finding the inverse Laplace and also finding the poles of a transfer function. So the inverse Laplace of 1 upon s square plus 1 is sine t u of t. So we have to plot the graph of sine t u of t. It is very simple. We all know the sinusoidal signal sine t u of t. Now since there is a u of t is a right hand side signal, so we have plotted sine t only on right hand side of the signal. Now we know sine t, cos t, these are all sinusoidal signals and all sinusoidal signals have some oscillations. Now this sine t have an oscillation. Oscillation means the value of omega naught. Here the value of omega naught is 1. If you compare sine omega naught t with sine t, the value of omega naught will be 1. So every sinusoidal signals has some oscillations, and whenever the nature of response of x of t is sinusoidal, that is cos or sine, we have oscillations, and whenever there is an oscillations, the system is marginally stable. So we can say if any poles are complex, that is they lie on imaginary axis of S plane, then the system is marginally stable system. The location of pole was on imaginary axis. This was our pole location. Our one pole was at plus J1 and my second pole was at minus J1. So the location of pole was on imaginary axis. and the nature of response was sinusoidal. So whenever we have poles on imaginary axis, the nature of response will be sinusoidal, and whenever we have sinusoidal nature of response, the system will be marginally stable system. So let us take a transfer function x of s is equals to 1 upon s square plus 1 whole bracket square. The poles will be plus j1 and plus j1, and the second pole will be minus j1 and minus j1. Now this is my s plane. My first pole will be plus j1, then the second pole will be again on plus j1, third pole will be minus j1, and the fourth pole will be on again minus j1. So these are repetitive poles on imaginary axis. Now again, in order to comment about stability, first let us find the inverse Laplace transform of 1 upon s square plus 1 whole bracket square. So its inverse will be t multiplied into sine t u of t. So x of t is t into sine t u of t. So let us plot this x of t. First we have a t signal. This is the way to plot a t signal. Then we have to multiply this signal with sine t u of t. Now we know sinusoidal signals are marginally stable signals because there is an oscillation, but this sinusoidal signal sine t u of t is multiplied with a t signal, and a t signal is not absolutely integrable. A t signal is not absolutely integrable. The value goes on increasing. There is no any finite value. So when these both signals will be multiplied, the final result will be an not absolutely integrable and unbounded signal. Hence we can say the system will be unstable system. So any repetitive poles lying on imaginary axis of S-plane, then the system is unstable system. Now this is interesting. The location of pole was repetitive poles of order n. Then the nature of response will be t raised to n minus 1 into sinusoidal signal. Our order of the poles was 2, so it was t raised to 2 minus 1 into sinusoidal signal, so it was t raised to 1 into sine t u of t. Now let us go to the seventh, which is complex poles on left hand side of imaginary axis. Now what will be the stability if the poles are complex and they lie on the left hand side of the imaginary axis? For this, let us take a transfer function x of s is 1 upon s plus a whole bracket square plus b square. Now the poles will be, our first pole will be S1, it will be minus A plus JB. The second pole will be S2, which is equal to minus A minus JB. Now we need to plot these poles on the S plane. First, I want to plot the real part. Real part is minus A in both the poles. So I'll plot the minus A. Then I have to mark this plus JB and minus JB. It will be on imaginary axis. My plus JB will be here and minus JB will be here. Now let us intersect these points so that we get the first pole minus A plus JB here and the second pole minus A minus JB over here. So these are complex poles on the left hand side of the imaginary axis. Again, to comment upon stability, let us first find the inverse Laplace of 1 upon s plus a whole bracket square plus b square, and the inverse Laplace will be e raised to minus at sine bt u of t. Now again, we have already discussed the Laplace transform in some previous lectures. I will be sharing you the link of the Laplace transform video in the right side of the I button. Now just for an example, we have studied e raised to minus at sine omega naught t u of t. Its Laplace transform is omega naught upon s plus a whole bracket square plus omega naught square. Now again, if you compare both this, the value of omega naught is b. So omega naught is nothing but b. So only in place of omega naught, you have to replace b. So it will be e raised to minus at sine bt u of t. This is the same answer that we have written. Again, I am telling you, when we will solve some good questions, there we will study about how to find the inverse Laplace transform. There is a method called partial differentiation method to find the inverse Laplace transform. Also in partial differentiation, we have three types. So we'll discuss all of them when we start solving questions on this topic. Now our aim is to draw this signal e raised to minus at sine bt u of t. Now I have e raised to minus at. We know this is an exponentially decaying signal. So I have drawn the yellow line which shows this is your e raised to minus at u of t signal. And this is the mirror image of e raised to minus at ut. So we have drawn e raised to minus at ut. Now we have to draw sine dt. So we have to draw a sinusoidal signal in this exponential signal. So it will be something like this. So at some instant of time, the signal will become 0. Hence, we can say it is absolutely integrable and it is a bounded signal. Hence, it is a stable system. So we can conclude if any complex pole lies on the left hand side of imaginary axis of S-plane, then the system is a stable system. Again, the location of pole was complex, which has a real part and imaginary part, and the nature of response is exponential and sinusoidal. For this example, our poles were minus a plus jb and minus a minus jb. So whenever we have complex poles, that is real part is minus a, and an imaginary part which is jb, then the nature of response will be exponential and sinusoidal. We got the response as e raised to minus at sine bt into u of t. Now let us go to the last point, that is complex poles on right hand side of imaginary axis. For this, again I have taken a transfer function x of s is 1 upon s minus a whole bracket square plus b square. The poles will be plus a plus jb and plus a minus jb. So we have to plot these poles. This time I have directly plotted the poles. We have the real part plus a in both the poles. So plus a, and the pole will be plus a plus jb, and one pole will be plus a minus jb. Now again, to comment about stability, we have to find the inverse Laplace transform, and the inverse Laplace transform will be e raised to plus at. In earlier example it was minus at, now it is a plus at sine bt into u of t. Now we can plot this signal. Now e raised to plus at is an exponentially increasing signal. So it is something like this. We have to draw the mirror image as well. And between these signals, we have to draw the sinusoidal signal. And yes, you have correctly guessed, this is not absolutely integrable as the value is increasing of the signal, and also it is an unbounded signal, hence this is an unstable system. So we can say if any complex conjugate poles lie on the right hand side of imaginary axis of S-plane, then the system is an unstable system. Again we will be having the same thing, location of pole, these are complex, means they have a real part and imaginary part, then the nature of response will be exponential and sinusoidal. So I think it will be quite clear for everyone. If you just know the value of pole, you can plot the pole on the S-plane and By plotting the pole on S-plane, you can easily comment about stability, whether a system is stable, unstable, or it is an marginally stable system. So this was about stability of system. In our next lecture, we will discuss from poles how can we find the time constant tau of a system, and from the value of poles how can we find the frequency of oscillations. So let us discuss these 2 points in the next lecture.